Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you look for videos explaining topics in college mathematics courses, please consider subscribing because you're in the right spot. And let's get into the current video. I want to take a look at what is called the set of loops in a topological space. So first of all, let me give a description of that. Let's say this is my topological space X. A loop is going to look like the following. Let's say I've got a point, I'll call it Q, and let's say a path, right? Remember, a path goes from the closed interval 0, 1 to X. And let's say it starts here and also ends in the same spot. Okay. Pictorially, this is what a loop would be. It's going to be something, a path, a continuous path that starts and ends in the same place. Therefore, let's give a definition for that. A loop in a topological space X is a continuous function f, which goes from 0, 1 to x, where f of 0 is equal to f of 1. In other words, the starting point and the end point are the same. All right? And in this video, this is going to be sort of our main sort of concept that we are going to look at is what about the set of these things in a topological space. Therefore, let's introduce some notation. So notation. Okay. Omega x q. Okay. Omega xq is going to be, let me kind of write this out in words first, is the set of all loops in X based at Q. When I say it's based at Q, Q is the starting and the ending point of this, and therefore we can write this a little bit more formally as it's the set of all functions that are continuous from I to X, such that f of 0 equals f of 1 is equal to Q. Okay. So this is the concept behind a loop in a topological space, and in this video we are going to be concerned with the entire set of those. Let's start by looking at a specific example of a couple of loops. Okay. For example, let's say f of t is equal to, let's say, cosine of 2 pi t, and the second component is sine of 2 pi t. Okay. And this is going to be a loop in R2, and the graph of this, of course, the starting and the ending point are both at the point over 0 up 1, and the path looks like this. Right, so this is a loop with base point Q, which is over 0, over 1 up 0. So that would be the base point of this loop. Similarly, I could say that G of t, which is equal to simply the point 1, 0, is also technically a loop at that same base point, because this is a continuous function. It's a constant function, but it's a continuous function, again with the exact same base point as f. Moreover, I can define h of xt to be 1 minus t f of t plus t g of t. And what this is, this provides a straight line homotopy from the function f to the function g. Therefore, h is a homotopy from f to g. And what this shows me is that f is in fact homotopic to a constant function, which is going to be sort of the basis or the content behind the next definition. Okay. Definition. The notation C with a subscript Q is an element of the loops in a topological space based at Q, where CQ of X is equal to Q for all let's see, actually it'd be CQT because it's a function from T, or from I into X. So this would be CQT for all T in I, called a constant loop. Okay, so this is called a constant loop. And any element of omega xq, which is homotopic to CQ, is said to be null homotopic. Therefore, a loop which is homotopic to the constant loop is null homotopic. That means that this loop over here, which the path is, this unit circle, is homotopic to the constant loop at the same base point. This is a null homotopic loop. Now, okay, so great, but what does that mean? Well, here's what I want to do is I want to kind of get ahead of myself just to kind of give you an idea of why these things are going to be useful, or why these things in a theoretical context are going to be so important. So looking ahead. All right. Let's consider two different topological spaces. All right. And within those topological spaces, let's say that I have a loop based at the point Q. Let's say this is the point Q, and let's say I've got this loop here. Okay. Same thing over here. I've got, let's say, and it doesn't have to be the exact same loop or anything like that, but let's say I've got this loop based at Q, which looks like this. So within these two topological spaces, I've got a loop based at Q. Now, what I'm going to do with this, so I'm going to kind of add something to this one here in a moment, but let's take a look at this first topological space. If I take this, I can see that I could, I could continuously deform it into the loop at Q, so in other words, a constant loop. So therefore, this loop would be null homotopic. Okay, great. Now, what happens if this topological space over here, this one that I'm going to make a little bit different, what if this has a hole? Right? What if that has a hole in the middle? Well, I cannot continuously deform this loop to a constant loop. So I could start to deform it, right? I could, just like I could over here, sort of start to shrink it a little bit. But I cannot continuously get past that hole to deform this to a constant loop. Therefore, this loop here is not null homotopic. So right here, this already kind of gives me an idea of why these things are important. Loops that are not null homotopic are actually going to detect holes in a topological space. Okay, let's go ahead then and show you some other things here. In previous videos, I've mentioned that this concept of homotopy, path homotopy is an equivalence relation? Well, let's mention it again. Path homotopy is an equivalence relation on the set of loops in a topological space based at Q, and hence partitions the set into equivalence classes called path classes of loops. Okay. So what we did is we actually partition this set of loops using this equivalence relation. And now I've got this new set which consists of equivalence classes called path classes of loops, which I will denote. So called path classes of loops. The resulting set can be denoted omega x q and then modulo that equivalence relation. Okay, so modulo the equivalence relation, and this is actually a relative equivalence or a relative homotopy because everything starts and ends at Q. But again, whether we put that on there or not, it's set of equivalence classes with respect to homotopy. All right, now what I'm going to do is I have this set of equivalence classes. I'm going to define an operation on it. We are going to define a multiplication on these equivalence classes okay. So I'm going to define an equivalence a multiplication on these equivalence classes that will then lead into something called, well, wait till the next video. It's going to be extremely important. All right, so here's what I'm going to do. I'm going to say, let's let F and G be elements of this collection of equivalence classes. Okay, and we're going to define the product of those two as follows. All right, let me clean this up and illustrate how I'm going to define it. Okay, I'm going to define this in an informal way using diagrams, and I'll do it a formal way using actual function definitions. So informally. All right. These two are elements of this this set of path classes of loops. So F and G are individual loops. So I'm going to take, say, F is an element of this and G is an element of this. And again, they're both loops at the point Q. So let's say I've got this point Q, and at that point I have this loop F. And I also have another loop at that same base point that I will call G. And again, this is any element. These are any elements of these two equivalence classes. Of course, if I pick a different element of this one, it's going to be homotopic to it, so the same sort of properties are going to apply. But the idea is that I want to define a loop using both of these two. Now, before I sort of write anything, let's just sort of talk through it. How could I come up with another loop that uses both f and g? Well, I could follow the path of f at double speed and then immediately follow the path of g, again at double speed. So that way the entire path is followed throughout t going from 0 to 1. So 0 to a half would follow the path f at double speed. A half to 1 would follow the path g at double speed. That would then create one loop using both the function f and the function g. Now let's do this in a more formal way. All right, I'm going to define f star g as follows. I'm going to say the equivalence class of f multiplied by the equivalent, stand over here, times the equivalence class of g is equal to the equivalence class of f star g, where f star g of t is equal to the following. Well, it's going to be f of 2t, right? F of 2t when t is an element of 0 to a half. And it's going to be g of 2t minus 1 when t is an element of a half to 1. Notice both of those overlap when t is a half, but this would be f of 1, which is q. This would be g of 0, which is also q. So therefore, even though they overlap in the domain restriction, the function values are the same thing. So either way, it's q. This follows the path f at double speed for the first half of the interval. This follows the path g at double speed for the second half of the interval. And therefore, this ends up being a loop based at q. So what I have is the set of loops. I form it into a set of equivalence classes. I then form an operation, which we call multiplication, on the set of equivalence classes. And this is going to have various properties that we will explore in the next video. So stay tuned, and thank you for watching. Please consider subscribing.